My glasses are dirty for some reason. Hello, everybody. Sorry, I'm just cleaning my glasses real quick because for some reason they are all hazy. Not sure why. Okay. Welcome, everybody. Yeah, been a while. Been a little busy. Hey, Cat. What are you doing here? Hello. Come. Yeah, you want a snack? See if we can get you on camera for a sec. Come on, Cat. Come on, Misty. Here you go. Another one? Here, come and get it. Come get it. Come. Come on. Come on. What's wrong, her? See if we can get you a bit closer. Come here. Come. Come on. Come. Come on. Yeah, you can do it. Is it really? You're normally not that scared to walk on my desk. What's wrong with you? Come. Right, I guess. I don't think the camera is going to catch anything low enough for that, so you're going to be probably underneath the camera. There you go. Now I can do this. Come on, push. Yeah. Oh, yeah. Here. Come on. Come grab it. Come grab it. Grab it. Yeah. She doesn't want to. Come on. Come on. See. You know, you're hardly on the camera now. Come say hello. Hello, everybody. It's my cat. Go, 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 go. Scaredy cat. Doesn't like to be on stream. Sorry for that weird start of the stream, but yeah, that's what I get when the cat's coming to say hello. She can come and say hello on the stream. Okay, yeah, sorry, it's been a little while since I streamed. It's been a very, very busy time over here. Gonna be one of the cameras there, my screen is there. Very annoying. What are you doing now, Puss? She is going to distract me all night long. I know that already. Okay. So, oh, I think my sound is blowing out a little bit, so let's turn that down slightly. Anybody in chat, let me know if the sound is good enough, or if it's too loud or too soft. Well, it shouldn't be too soft because it's pretty much maxing out according to OBS. So, all right, tonight we're going to have a little bit of a look at, well, we're going to continue looking at custom shader templates. Of course, last stream, I actually was working on implementing a shader template to show how that works. But since then, Godot 4.3 was released, and the moment Godot 4.3 got released, we merged a whole bunch of outstanding work that we didn't want to risk delaying 4.3 even further. And a lot of that work also ended up messing up my PRs, which is pretty normal because things get merge conflicts. So we need to go and correct those. And we'll just see how far we can get tonight. Now, I'm not going to make it too late. It is currently 9 p.m. here, and unfortunately, I have a very early morning tomorrow morning. So I need to make sure that, yeah, that I take enough time. Can't stop playing with my internet cable. Luckily for my other laptop. So I guess my son's going to be unhappy tomorrow that his laptop won't have internet. Buzz, hey, don't do that. Don't do that. It's not a toy. I guess hopefully that'll keep her entertained in a while. I need to buy a new cable for that one anyway, because that one's way too long. So that's a fine have an excuse. Anyway, as I was saying, I need to wake up early in the morning because I've got a Motocana day. So we'll see how late we make it, but definitely not past midnight. But we'll see how far we get. So we have two PRs that we're going to be looking at today. The first one is this one, the add build to include building include scripts. And ability to include built-in include files. Thank you, Baz. I'm so happy that I can talk. Why is my cat all of a sudden super active? Anyway, I hope she's not making too much noise in the background. So this is the first part of two PRs that are involved, and this PR simply adds functionality that we allow the shaders, the built-in shaders, the include files for the built-in shaders, to also be accessed in custom shaders, which is kind of important. And that doesn't just work for shader templates, that works for other things as well. So this is still open from when I was working on good old OpenXR. So just to illustrate, when we look at our servers, rendering, renderer RD, we will find a folder called shaders. Inside that folder, and I'm just going to unfold these a little bit, we will find all sorts of shader codes that are built into Godot that form the core of Godot. We will find these two folders here, forward clustered and forward mobile, that contain specific code for those renderers. And what we can see is that we have various include files here. So that's the cluster data include, and here we have the light data include, etc., etc. Now, one of the things that, or the only one that I think I'm using as a test include in that PR that I showed is the scene data include, which is the structure of data that we make available. So every frame we update this, and we get our projection matrix, the inverse of the projection matrix, the inverse of the view matrix, and the view matrix. Then we have additional versions of the projection matrix and inverse projection matrix per eye. This is for multi-view. So in mono, those will match the ones that we have up here. But in stereo, these will be based on a central camera point, and these two will contain the specific matrices for each eye. And there's a bunch of other information in here. So this is actually a structure that we include in our main renderers and our main scene renderers, and we're slowly also including in other parts as well, because we have a lot of duplication right now that we're slowly trying to optimize. But this is also very handy in, for instance, in, is that going playing? Oh, someone noticed that I have a stream. This is also, for instance, handy in what they called compositor effects. So in compositor effects, you're obviously doing post effect. You might still want to have access to the inverse project matrix so that you can take a coordinate that you are updating in your compute shader, and you want to unproject that so that you know what place in the scene that pixel goes for. Yeah, I guess that maybe the white background is indeed a little bit too much for streaming. I do prefer white myself. No, that's not a profile, but indeed, I guess that is for that for streaming might be a little bit overdone. But where do we change that? Where is that? Come on, VS Code. Oh, by the way, hi, this is Alex. How are you going? Oh, here, theme. Haha. Color theme. So we are currently on light modern. Light, that's all light. What would be the difference between all these different dark themes? Well, let's go here. So, okay, well, hopefully that's a little bit better for those people who are watching the stream. Also, let me go and turn this thing off. There we go. That's a little bit less blue light. I have a little. I actually bought a Elgato prompter. And that's something that I'm going to start using for some of the YouTube videos that I'm hoping to do in the very near future. But it went to a blue screen just now because I'm not using it. And every time my computer goes to sleep and wakes back up, all of a sudden the teleprompter turns back on. So I probably need to figure out a nice way to have a proper off switch on that thing. Anyway, not to get too distracted, I am in the wrong place again. Why is that going like that? We were talking about our scene data include file. So yeah, it would be very handy to include that in your composition effects shaders. It's currently not possible. And that's part of what this first PR does, not just, you know, preparing a number of things for... Cat, what are you doing? What are you playing? He is really making noise. Again, apologies if my cat is making a lot of noise in the background. But, you can actually, from the source code right now in the current build of Godot in 4.3, you could copy this and paste it into your shader. And then through the scene data object that is passed into the composite effects, you can actually make sure, because it's already loaded into GPU memory, you just need to get the UBO from the scene data and then assign it to whatever entry point you have or whatever uniform you have exposed this with, and you can get access to the data. You do need to, if you want to do that right now, you do need to go and check how it's included here in the scene forward clustered inc GLSL. So if we find, oops, not there, in here, scene data, and let's not do that. We can see that the scene data is included twice. We can see that we have a block here that has two entries for scene data, a data and a previous data. This one is always used. This one is only used if you got motion vectors turned on, and that contains the previous frame's data so that you can do comparisons between all the new, and that's how the motion vectors are filled in. So basically, you need to therefore include that data structure, and you need to include this little bit of code, and then you need to set that uniform with the uniform ID that you're going to get from the scene data object that is passed into your consumer effects. And Cabalscap actually uses that. He did some experimenting with that, and he added it in. Now, with this PR, the one that we are currently looking at, you can actually include that file directly into your compositor effect by just doing include scene data, and it will include that file for you. That is the whole purpose of this, and we do that by in the SE sub, we actually compile in every one of the include files that we find, but then more importantly, in our renderer, we do go and register the include files that we want to have access to with a nice little name that they become accessible through. What are you? Crazy cat. So yeah, that is basically what this PR is for. And this PR basically creates the structure for being able to include those files, because of course they are not files. They are files in a source code, but they're actually not files when you are running a Godot application. They're actually compiled into the Godot exe. And that's the same thing with the normal shaders. And the interesting thing is that when you look at, for instance, the scene forward clustered GSL shader here in our forward clustered shader files, this is actually our whole default shader template. That's a lot of code that is run whenever you are rendering a 3D model on screen. That's that one. Now, you can see that actually does a bunch of includes. So it does our forward custom include, and inside of that, that's in this file. There's a bunch of includes here, and there's another include there, and you'll find a bunch of other includes in there. Now, what happens when we compile Godot is we don't actually have all those little bits inside of the exe. What we do as a preprocessor, as part of the compilation of Godot, is load this file and actually pre-process it at that point in time, which is ending up like this beautiful little thing, where you actually see the end. You can actually see it here. It's the whole end result of that shader is, it's all parsed. So that is actually the full shader code for that one. So what we're basically doing is, that's now compiled into Godot. And we're doing the same thing with the separate include files that we want to expose to users. Now, at this point in time, in this PR, it's only those three that I mentioned about. These three, the scene data, light data, and decal data, put them the wrong way around. So those three are just included in this, but we're going to be including many more. And we'll look at that tonight as well, because like I said, we're first going to do this PR, but after that, we're actually going to go and have a look at the shader templates PR and update that so that that is all working again. And in there, we actually start breaking up our clustered shader a little bit, and you can actually see some remnants of that. Here's some old generated files from that PR. So we'll see that we'll break those things up, and that's part of what we need to fix up because some of those have changed. And that's also a big difficulty with this PR. If we don't merge it within a relatively short time frame, there is a risk that someone changes the code in the clustered shader, and we suddenly have a mismatch again, and we might lose code. So I'm a little bit concerned about that. That's going to need quite a bit of testing before we go there. The other thing which we're going to do is, this is the initial little bit of breakup that we will do as part of the shader templates PR, but we're actually planning to do much more. So we really want to turn that scene forward cluster GSL file, all the code in here, we want to actually include into separate include files that are usable, that you can then include into your shader or your custom shader template so that you don't have to rewrite everything unless you actually have a reason to do that. So for instance, if you want to use Godot's built-in lighting code, you can just include that and then start using it. If you do not, if you want to create your own lighting code, you will be able to ignore that include file, write your own code, and go from there. So it all depends on what you want to do with the shader templates, how much of that code you want to include. But it is going to be important that that first PR is only going to do a basic breakup of some of the basic components, and a lot is going to remain inside of that clustered GLSL file. And the same thing, of course, with mobile. This all, by the way, only applies to the Vulkan renderer, or the render device renderer, I should say. So DirectX and Metal will piggyback on this as well. But mobile and forward are the only two that we're going to be doing this with. We're not going to be doing this at this point in time with the compatibility renderer. May do that in the future, but not yet. All the framework for that is done, but there's a lot more work to do on the compatibility renderer. That makes that task a bit harder on that renderer. Okay, so introduction all done with what we're planning to do today. So I've already checked out my built-in include. So that is this little puppy here. However, I haven't rebased it yet. So I think this one will actually rebase pretty decently. However, I want to move some of the code that's in the other PR into this one. So we're going to have a look at that and see how easily, how easily we do that. So let's go and rebase out of master. Obviously, I've already pulled master. And there we go. That's actually a lot easier than I thought. And I wasn't really expecting problems with this one. Let's just at least make sure that we can still build it, that there's no hidden surprises here. And what I want to quickly do, because it's been a little while since I last worked on this specific PR, I just want to go and have a look if there's anything weird in here that I might need to change. No, that's just my hash map that I put in here. So I'm pretty sure. So this is basically, and this is the other problem that I have with this, that I might need to do better. And I haven't really decided yet what the best way of this is. But we have several points in Godot where we pre-process shaders. This is the final part, where this is basically the code that gets run whenever you are importing a shader through GDScript code. Or I should really say, if you have a GLSL file in your project, this is what parses that and makes sure that you can, compile a compute shader with that, or any sort of custom shader that you want to do. And this is really at the last possible moment where we do include files. And there's other places where we actually need to do that earlier. So I think in this one, it's only that what we're doing. Yep. But then if we go and have a look at the other PR that we're going to be working on, we are adding similar code in some other places here. And I need to just find that, because that's the part that I want to actually move into that first PR. So that's all the shader template overrule code. Ba-ba-bum. Ba-ba-bum. Let's see if we can find it. There's too many things. So that's all the resource loader stuff that is changing. That's the additional logic on our fragment shader. Very good. Yeah, we go to 24 bytes instead of 16. That's another one that I'm not 100% sure is going to cause us some problems, but that will come out of the review. That's what the update template. Sorry, I need to find which little bit of code I still want to add in there to make my life easier. So this is where we have the other include files. Now, obviously, the other include files, there's quite a bit that we need to do. Is it in the clustered CP? I don't think it's in here. Oh, that's all the, yeah, that's the big changes on the, and that's also something I'm worried about. That's going to probably cause us grief in rebasing. But we'll see. It's going to be very tricky making sure that we don't lose anybody else's changes with this. But again, that is why we test and why we review, making sure that, and this is also where we're going to be making use of, actually, that's a bad thing because the other commit is in here. So let's just go and filter out that we don't get that in there. And it's not going to be there. Is it? Because this is where you actually can make good use of GitHub in updating this in a minute and then looking at, okay, what has it changed? And does it look like we're going to be missing something because things have moved into another place and Git merge hasn't picked up on the fact that we have those changes. So this is the code that I'm looking for. So in shader templates, that is my new code. So that's fine. That's bringing stuff in. That is indeed already parsing some of the include stuff. So that is going to be part of the new PR. So that's all fine. But I thought there was another place where we did more of the include parsing. Yeah, it's been about a month ago since I wrote all this, so it's not completely, you know, don't remember everything of this. It's remembering what I've done. And it's still compiling in the background anyway. A good thing, it does run through the compile, so that is good. I think this is what I'm looking for. So this is when we are adding stages to our renderer. I also have part of the include logic. I think that is one of the places that I wanted to add into here so that we already have that as part of all the include logic. Let's see. So that is part of the render itself. So I just need to go and collapse a few things. So that was, oops, too many files open. Renderer RD, shader RD. So where am I? Oh, I'm in storage. No, I don't want to be in storage. It should be somewhere down here. There we go. And the function we're looking for is at stage. At stage, very good. Oh, it's all the way at the top. Very good. So one of the things that we change here is we're actually caching our line counts because that will change. All right. And then in this big thing, and that's going to be right at the end here, we're going to go and copy this over. And that is going to be here. So what this bit of code does, oops, there we go. It checks if our line, so this is basically some code that parses through our shader logic line by line, and it's breaking everything up depending on, or it's actually creating chunks depending on markers in our shader code. So for instance, if we look at our, hey, Big MacBook, how you going? Thank you for joining. So if we go and look at our forward cluster GLSL file, all the way at the beginning here, you will find a keyword hash version defines. And when we see that line here, we're going to mark that chunk as the type version defines chunk. And that ensures that we actually insert a whole bunch of things that we are defining in code. So these will contain our defines for our shader version. It will have our defines for our global setups, or whether we have multi-view support, or whether we have how many on the computer shader, how many things, how many work groups we can have, and that sort of thing. There's a whole bunch of defines that get inserted here, and I'll show later on in Godot how you can look at what it actually is inserting there. I actually had that in my previous stream. We looked at that a lot, but I'll revisit that once we have a working version of this. And the same thing, it finds our hash globals, and then it actually has a couple of different types here, depending on whether we are parsing the vertex shader or fragment shader or compute shader. And it's all so that it can insert things. So we got some for uniforms. I'm quite sure. Oh yeah, the hash code is where we are inserting our user code. So when you're creating a shader inside of Godot, you create your vertex shader, your fragment shader, and your light shader. Those are just little fragments that get inserted into the shader template. So this is where that handles. And then the new little bit that we are introducing is that if we find the hash include, then we are going to parse that. Now, in this case, all the hash includes, like this one, have already been parsed during compile time. Like I said just a minute ago, is here we get our final version with all our includes already parsed. So for our built-in shader, this code does nothing because all includes are already parsed. But for our custom templates that we're about to introduce, obviously we do want to parse this in there, because they will not be coming from anything pre-compiled. We will be compiling those as part of the source code, or as part of the user source, as part of your game source. So all this does is find out that there's a keyword include, and then it looks up in this has built-in include file. So in the rendering device, we keep a dictionary of include files. We check if that exists. And if that exists, we insert those lines into the shader, and then they just get processed like normal. That's all that little bit of code does. So even though this doesn't do anything specifically for this PR, it doesn't actually add any logic. It prepares logic for the what do you call it? It prepares logic for the custom templates. And I just want all that stuff in that one PR just because it makes it easier. I do not know why I am including that. Am I including that because I'm accessing it anywhere? Or was I going to access that anywhere? I don't know why I put that in there. I have a feeling that that is not needed. So we can clean it up. Need to make a mental note that we clean it up when we look at the other thing. I think that I might have added this in as something that I was originally going to do. I was probably originally planning to put it into material storage, but I ended up putting it into render device. Yeah, so that change we probably need to undo. But we'll deal with that later. So here we got some more include, but that is something that I want to keep there. That's fine. And that is all stuff that belongs here. Okay. So what did we do in material storage? That's all the shader template stuff. So that has nothing to do with the shader RD. Okay, that's interesting. Well, look at that. We might actually end up cleaning a few things up over here. That is really nice. No, actually, what do we do in particles? Oh yeah, that's just everything now has that shader template thing, but it gets ignored in most of the other types. That's more for in the future, that if we want to do shader templates and support that on Sky Shader or in particle shaders and want to overrule the built-in shader template, then we have the framework for that. Just currently it's not supported. I'm only focusing on the main shader template. And even this initial PR only does it for the forward clustered. And I'm only going to do the mobile one if this is all okay, because also I need to start maintaining 2 different renderers, and that's crazy. It's better to fix up one renderer first and then go for the other one. So let's go and build that one more time, see if this change that we just did isn't going to screw us up. It looks all right so far. Okie dokie. Sweet. Okay, cool. Alrighty. So now, I don't actually want to use you. That's not a good idea. Don't actually think I want to use that. I might actually want to try and see if that one allows me to test it. I might actually have a change on that one. So let's go and run our editor and see how that works. Because if I remember correctly, I changed this this demo to include using that scene data. But I could be wrong. It's been a while. Boom, 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 boom. Okay. No, sorry, I just need to move that over here. So this is my little demo for that. I also want to go and change my layout to that one. So I've moved my file system over here just to clear this up. I now only have one set of things here. Means also that my camera on the right shouldn't be obscuring things most of the time. So this is my preferred layout of the Godot editor. And especially, you know, one of the things, of course, is I actually have a widescreen monitor. I'm only using about just a little less than half of my monitor for the stream right now. So I need to keep resizing every time that I start Godot. But definitely on a big widescreen, this is really nice because I got the maximum amount of space for my 3D viewport. So yeah, that is something that I do enjoy having. Now, where are we with this? So world environment, let's make you a bit bigger, make you a bit wider. So we can see that we have a compositor set up, and I've actually got 2 compositor effects in. The grayscale is currently enabled. And this is just a test one, which is disabled. So if I disable that, it's back to normal colors. And if I enable that, then, oh, that is really bright and washed out. But yeah, I'm inverting here. So these are just 2 examples that are in here. But I thought that I had made an example as well for using, maybe I have not currently got that checked out. So that might be worth having a look at. But yeah, there's 2 examples in this project. For anybody who wants to know, by the way, because I know that I sort of keep assuming that everybody knows about this. But we have a Godot demo project repo on the official Godot engine GitHub. And that has a whole bunch of demos. And in this case, there should be a folder here, compute, exactly. And there is a folder here called PostShader. And in PostShader, we can see that we have those 2 little demo versions. So there's a grayscale, which is just a full compute shader that does grayscale. Just as an example of how you would set that up. And then there's a separate one, which is called this process shader GD. You can notice that there's no GLSL file for that, because the GLSL is actually stored inside of this shader over there. And you can see that there's a little hash marker in there where we then insert the little bit of code that you actually specify over here. So now all of a sudden you have a post-process shader that you could just copy some simple code into. So if you're interested in compute shaders and using those for compositor effects, this is where you look at how that works. However, I thought that I had a version that expands on this. So maybe that is still an outstanding PR, probably is. What about a shader example to show build and includes? Look at that. So the demo build and includes, that means that I'm going to have a quick look. 1 second. All right, so we can see that I'm actually on a different demo with edit this project. So I'm just going to have to, let's actually exit out of this for a sec. Because I never like changing branches while Godot is open. Why are you not exiting? Don't save. I don't have to keep these changes. So there we go. And now we can say, check out, what is that called? Demo build includes. So now switched over to that. You can go back over there. Where are we? That's right. Let's go and try that. I still have to try out composer. Yeah, big MacBook. It is fairly complex, especially to get into. Yeah, it starts the right size. It's gonna remember it now. Did someone fix that? Oh, that's gotten fixed. Oh, how nice. I didn't know that they've done that yet. That was one of my complaints from my streams a couple of weeks ago where I said, why does it always have to go full screen? And it's now remembering the last place the editor was moved to. I don't know who made that change, but you're a godsend. Perfect. Super happy about that. So that's going to make my life a lot easier on stream. I will only now need to resize it one time because I will be putting it back on full screen when I'm normally developing. Huh. But I'm pretty happy about that. So, what was I saying? Oh yeah, so big MacBook, yeah, it is. It's very much worth playing around with compositor effects. You can do a lot of cool things with it. This demo that I'm showing is a good starting point to sort of learn the basics. I believe that I've even got a little guide on the in the manual that sort of talks through, I think, this grayscale effect. And been a while since I wrote that, so I'm not completely sure what I did as an example there. However, we also, just so that you're aware of this, and this is actually something that I do have a stream from a couple of months ago when compositor effects were still called rendering effects. So there's a few small changes since then. But I do have a demo. And I know, not that one. Where are you? Here we go. RE, radial sun rays. Yay. So this is a much more advanced demo that is using compositor effects for a God ray type of effect. Now, I don't claim to have invented this. Actually, nice to link to it. It is based on an explanation from Harry Aliza Vicus. Oh man, I butchered your name there. I'm very sorry, Harry. But yeah, it is a really cool effect, and this shows a much more complex set of things that you can do with compositor effects. Cutting a hole through an object. I'm not quite sure if you could do that with compositor effects right now. Because you probably need stencils for that, and that is something that someone's still working on. I'm not quite sure if that will be possible at the current state of compositor effects. But hey, look into it. You never know. I could be wrong about that. Anyway, so this one is now using that the built-in thing. So we're still doing the grayscale by default here. So if I turn that off and I turn this new one on, you can see that we got these funky colors. So what do these funky colors mean? Well, if we go to the source code here and we go to our post-process shader GD file, I'm going to go and make that a bit bigger. And can I please hide that? There we go. What is zoom? Well, I hope that text is large enough for everybody to read. But what you can see here is that the default template code is a little bit more elaborate than what we had before. But the most important thing is that we now have this in there. So we have an include scene data inc GLSL, which we now know from our PR that we're doing there we go, is including our scene data include shader, which is that shader that has that big struct in it. What we do not see is that we still need to go and copy this over out of the source code. That is not automatically inserted into the data include because the different renderers set that on different bindings, and we actually want to define our own binding for our shader. So if we, no, actually I want to go and look that up here. So if we go into, am I still have that open here? Boom. No, it's in this one. And then here we go, scene data. So you can see here that in this one, we're actually binding that to set 1 binding 0. And I think the mobile renderer probably does the same. But because we don't use set 0 in our post effect here, we're actually binding that to set 0. Now, those are just little registers in your shader that you can hook uniform data blocks into. So, you know, they don't have on any meaning other than the meaning that you give this. But that is why this little bit is still copied. But the most important bit is that the definition of a scene data is now being included here, which is made possible by the PR that we're looking at right now. The other bit that is important here is if we go all the way down here where we're actually running our effects, we can now see, first of all, that from our, now we're getting our, oh, that's the type. We're getting our render data in here. This is a struct that gives us access to all sorts of current information of the current frame that we're rendering. And what you can see here is that we're getting our render scene buffers. That gives us access to the buffers that we're rendering to. And we're getting access to our render scene data, which gives us access to that data structure, that struct that we want to use. And then if we go a little bit more down here, what we can see is that we define a new uniform here, and we're setting it to binding 0. So notice, oh, that was all the way up. We had our scene data uniform, but there were a couple of other uniforms that we had, and we put them all in set 0, but on different bindings. So we can see that we're adding our color image here so that we can read and write to our color image. And we are adding our depth image here so that we can sample from our depth image. So that's binding 0, binding 1, binding 2. And then for binding 0, which is our uniform buffer, we're grabbing scene data. So where is that coming from? Over here. So from that scene data that we got up here, so that get render scene data, we put into scene data. That has a function called get uniform buffer. So that's just an ID. That uniform buffer is already filled. It's filled at the beginning of rendering. We get that ID, we put that into our uniform. Here's our 3 uniforms. We create a set from that. We use our uniform cache from that. So even though we're calling this every frame, it's only created once unless something changes and we need a new one. And Godot automatically cleans up things when, you know, let's say that our we resize our screen, so all the buffers get destroyed, all new buffers get created. This ensures that at that point in time, because all our existing uniform and uniform sets are nicely cleaned up at that point in time, this grabs a new one at that point in time. But if we already have it, we grab it out of our cache, and we don't waste memory. So that's how we build our uniform set. And then finally, we bind our uniform set on to set 0, and that actually makes it possible to access that data from our shader. So, you know, in a nutshell, that is how you can use uniform buffers, and you can use them in your compute shader. And in this case, we now have our uniform buffer nicely coming from our scene data object, so we know that's already filled. We have our include file over here, including our definition, which also means that if in a future version of Godot we add more fields to that data, or we make other information available in that scene data structure, this doesn't break. You know, you don't have the wrong structure embedded in your shader because you wrote it against an older version of Godot. So this makes your implementation fairly version safe for the most part, unless we do something dumb like take things out or you know, deprecate fields and they no longer have the values that you're expecting. So there's a lot that we can do. Other than that, this still stays pretty much the same. So here's our binding 1 on that same set 0, which is our color image. And then here's our binding 2 on our depth texture. That's a sampler. So an image, we have direct access to the image. We can read and write. We can't turn that to read only or write only, which is in certain situations very important. If that is not marked, you can read and write both to it. But we don't have the ability to do, for instance, sub pixel fetches and that sort of thing. Hey, Unity Adventure, how you going? Hope you're doing fine. Thanks for joining. You did that video the other day that I commented on, didn't you? The what was it? Just getting started with XR. Yeah, that was a cool video. That was a good one. Anyway, the other reason why we're using a sampler here is because with the depth texture, you are actually limited to what you can do in accessing that one. But yeah, the sampler in this case is really handy. The other thing that is really important to realize is when you're accessing an image 2D, you are accessing those with, yeah, no problem, Unity. So you are accessing UVs that are absolute. So if you want the pixel 100 pixels to the, or the 100 pixels to the right and 100 pixels down, you have to do IVEC to 100, 100. While with Sampler 2D, you use uniform UVs between 0 and 1. So keep that in mind, and you'll see that we actually do some work with that here as well. Because, for instance, besides our fixed uniform data that we're getting in here, we also do a push constant, what's called push constant, which is a bit of memory that we can push into our shader every time that we do a draw call using that shader. And you can see that here we're passing the size of the image that we're working with, and we're parsing the view. Now, do know that this is a float, and that's simply because we have to use them as float internally. Just saves us a conversion on the GPU part, and then we have to pad it out because, as I say here, it must be 16 bytes aligned. So yeah, it's and the alignment rules with push constants are they really can trip you up, and they're not easy to explain. And maybe I'll get into that in another stream. It might be fun to actually talk about all that sort of alignment stuff. But yeah, it's not always that intuitive. Oh, actually, I could do convert it to int here. So, oh yeah, that's right. The problem is that we actually don't have a good way of doing push constants in GDScript yet. So everything needs to be a float right now, which is why I'm pushing that in as a float. Because you could do a uint here instead. But right now with Godot, you can't set that data properly. So that's why I'm using floats at the moment. That is something that is going to be fixed at some point, by the way. There is someone working on proper struct support in GDScript for shader code. This is also very important. So when we're using, we're using compute shaders here. Compute shaders are being run in blocks, as you specify here. So for us, it's blocks of 8 by 8 pixels, which basically means that block is rendered completely in parallel. Every one of those pixels is being done by a thread on the GPU or an instance on the GPU. It's not really threading; it's a bad word for it. But that means that if my image size isn't dividable by 8, some of those pixels that I'm running my compute shader for might actually be outside of my actual image. So hence there is an extra check. Oops, I scrolled down too far. Hence, there is an extra check in my shader to say, hey, if I'm accessing one of those pixels that are actually outside of my image boundaries, just skip the rest of the code. Kind of important, or else it, well, it really depends on your GPU what else it does. Some GPUs say, okay, I'm just going to ignore what you're doing here. Other GPUs will throw an error and cancel your shader, and there's also some that crash. So be careful with that. Here we can see that we are normalizing our UV because, like I said, for image sampling, we can use the UV as is. Oh yeah, this one is, by the way, important. The global invocation ID, that tells us exactly which pixel on our image we're currently running our compute shader for. So that is an absolute coordinate. So again, if I want pixel 100 by 100, that global invocation ID will be 100, 100. and we can just image load that. But when we are using our texture function, if we're doing a sampler, we have to use normalized vectors, which is simply a matter of dividing your UV by the size of our thing. Now, why I'm not using my param size here and instead converting that back to vec2, I don't know. That is actually wasteful, but you know, because really that should just be that, just to save some cycles. I'm not going to chase that right now because I'm not working on the... yeah, you know what? We're going to check that in as a change. Why not? Small optimization. It's not really going to matter, but... anyway, so we're grabbing our color, we're grabbing our depth texture, we're running our compute code, and then we're storing it back in. Now, this is an example of how this all works. And the reason why I'm doing it this way, because that's actually the second part of this equation, is when we now look at our post processor, you can see that actually our code here is a little bit more bigger than it was before with our inverse. Because what we're now doing is we're getting that depth value that we just had, and we're getting our normalized UV, which is that UV that we calculated there. We just have to know that it exists. Because again, that's the other problem with this. We don't have a proper shader passer here, just like the normal built-in shaders. But we're unprojecting that so that we actually get our, or we want to unproject that. So for that, we need our inverse project matrix, which we are grabbing from our, from our scene data block. You know, that's that structure that we accessed. And then we simply go and unproject it, and here's our vertex now. Well, almost in world space, or it should actually be, no, it's in view space. We just need to divide it by W, and now we have a vertex. And all I'm doing here to visualize that is just dividing it by pretty much the upper end sizes of these, and that gives that beautiful color spectrum. So and it's actually, yeah, it's a bit hard to explain, but it's on the negative side, it's always going to be black because negative values you don't get. So on the positive side, this is all going to be high because this is all in the background, but it's really on the thing in the foreground here, and you can see that nice wash going from left to right on the X, because on the X we add red, so the further to the right, the more red it becomes. Then on the Z, I can't remember what's the color that we use on the Z. We're adding blue on the Z, so that's why this goes from dark blue here to lighter blue, and we are adding some green on the Y. But since everything is pretty much on the same Y value, we don't really see that other than a tint. But that's just a simple visualization to make sure that this is all working. That's really all that I'm trying to do here. However, as a solution, it's a nice little example of how this works. But as a full solution, this is obviously way too simplistic. And one of the things that I want to do, and maybe I'll do that on stream someday, that would actually be probably a pretty interesting series of streams. I actually want to create a post-process material and add that to Godot, where we can actually, first of all, expose different internal keywords so that we don't guess what our variables are. We actually know what our variables are. We can then use the shader compiler in Godot to actually help us compile shaders. And then most importantly for this is when we are looking at our code here, we are now always loading the color and loading the depth. So if I want to do a post process that only access the color buffer, I'm always having this overhead, even though I don't use it. It probably gets filtered out, but there's still overhead in grabbing that. I might want to have access to other things. I might want to have access to my velocity buffer if I have motion vectors. I might want to update some other information. So obviously with a material in Godot, we can make that bits and pieces that we include or exclude depending on what the user is using in their code. So there's definitely a far improved version of this that we could make by embedding a material-based post-process to Godot. So that's something that I still want to do at some point in the distant future, because this is a nice little example, but it's overly simplistic, and it can very easily be too little for what people want. But it's still a really good example bit of code. Now, the most important thing is we have verified that this still works. So I'm pretty happy with that. Now, we can't really test that extra bit of code that I put in, because obviously that is used by the shader templates. So yeah, let's go and check in this new version. First of all, we're going to go and update this. Oh, why is there so many more changes? That is because awesome information. If I send, could one use composer effect to render changes to objects or camera view when the camera is underwater? Player health, diff planet, atmosphere, etc. Some yes, some no. So it's important to know that currently compositor effects gives you a number of hooks in between the normal rendering passes that Godot does. For the forward cluster shader, you have your def pre-pass that we do. You get your after def pre-pass before what's it called? Let me double check. So we have then our pre-opaque pass that happens between the pre-def or the pre-def pass and the opaque pass. We get a moment that you can do something in between. Then once the opaque objects are rendered, you have your post-opaque pass that you can do, so you can access the buffers and do stuff. Then we render a sky, then we have a post-sky. After that, we have a couple of other little things that happen, like screen space reflections, for instance, happens at that point in time. We then have a callback part where we can do, before we actually do a transparent pass. And then usually most effects are on the post-transparent, because that's when rendering is all finished and you do the final bit. And you can use that, for instance, for full screen post effects like color grading, doing something with the depth buffer and the depth information. And you can do that much more efficient than what you would normally do. There's a lot of people who would draw a full screen rectangle and then process stuff. That involves a bunch of copying around with buffers and stuff like that. So this is a much more efficient way to do that sort of thing. So for instance, your example of an underwater camera, where you would usually do some sort of screen effect to make the water look murky and stuff like that. That's what this is really perfectly for. But you cannot currently do something on individual objects, because Godot doesn't track that sort of thing. So after the opaque pass, all the opaque objects are drawn, but that just gives you an end result. You can't really do a lot with you obviously you do have access to your depth buffer. You can enable that Godot creates a separate buffer that it stores all the normals in, so you can do some amount of post-processing based on the actual object data that is there, but it's rudimentary what you can do at that point. I wouldn't use it for drawing 2D stuff or anything like that. That's much better just to use the 2D things with it. So like, for instance, a health bar or something like that. So I don't know if that's what you meant by player health. But that is depends a little bit on what you mean, but you want to do some special effects on screen if someone's almost dying, like make it all red at the borders. This would definitely be very very good for that. But if you do want to show things like health bars and stuff like that, then obviously that's not for it. So yeah. Sure. Anyway, I actually want to close this now that we have oh no, I don't want to close that yet. I was too quick. I needed to undo a few things to make sure that we're back in the starting point of this. And we only have our fix that we've done. Bear with me for a second. Oh, I love that this thing now opens on the last. This is so good. So I want to go and enable that one, and then disable this guy. Oh, so that's our starting point. So, oops. So if I do any status here, okay, so now I have, well, let's actually go and do diff. So I have my my fix that we did here, and we have that we now went from 4.3 to 4.4. That makes perfect sense. I don't know why. Oh, that's because that's a demo that's not part of this. So we actually need to do a couple of things before we finish with this. First thing is we're going to go and add this in. That was a big mistake. Okay, I canceled that in time. No, that should. Oh yeah, because I'm not in. I need to go in the compute folder. That's why. I almost checked in the hand tracking demo as part of this. Okay, let's try this again. See, now we're finished much more quickly. There we go. So what we're just gonna do is, whoops, we're just gonna go and do that, which is perfect. But the thing that I want to quickly do, I thought that I closed you already. Let's go and close you after all. What I want to quickly do is copy that. Check out, is it master? I think so. Stream master. Perfect. Base master. And now it no longer complains about that because that is now part of our demos. Yay! There we go. And with that, our built-in demos updated. Cool. Let's go and move that out of the way. All right, so how are we here? We just have that, which is just our little bit of extra code. Cool. Perfect. Yep, precursor to shader templates. And then we can just push that in. I typed that in wrong, didn't I? There we go. Cool. All right. Where's my... So when we now refresh this, we have all this. There we go. Boom, 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 boom. Now we have all the include logic in there. Okay. Added rebased and added some more codes that is needed for custom shader templates. All right. Would you mind reviewing this? Merging. Or all right, just to I'll probably send it as a message to Clay, but at least this way that is all there. Okay, now for this little guy, it's going to get a little bit more tricky because we can't simply rebase that, seeing that this includes both our custom shader template commit and the built-in include files commit we just changed. So we're going to have to do that a little bit differently. So the first thing that we're going to do here is actually, we're not going to check that out. Custom shader templates. We're actually going to rename that. So we're going to say branch -m custom shader templates. And I would like to copy that. And we're going to rename that to custom shader templates alt. Very good. Because we are right now on our build includes branch. So we're going to create a new branch from that branch called custom shaded templates. Good. Okay, we're going to go back to that in a minute. I first want to go to our old one. And I want to go and copy our commit from that. And let me go, so I could put that somewhere. Okay, just create. There we go. That's not going to be saved until we need it. There we go. And then we're going to go back to that one. And now we're going to say git cherry pick this guy. And that's probably going to throw up some problems. Yay. Okay, very good. All right. So now we are going to have a really pleasant time trying to figure that all out. So let's go and find those. We don't need you anymore. Did I put so many of them in here? Yes, I did. So we're going to start with the shadal language. What has changed here that it doesn't like? Okay, what are we doing here? Yeah, that's all that. So what is coming in? Why does it think that needs to change? Okay, hold on. I want to go and look at the original code for that. Now we don't need this window anymore, so code. What are we looking for? We are looking for servers. Rendering. Where am I looking? Shadal language, CPP. And then we're going to go and find get token. Oops. There we go. Okay. What are we doing here? Because this is a neat new code that I added in. Oh, hold on. This is something that someone else already added in. Okay, let's go and have a look at that. So we're getting string logic here. Okay. And that becomes a string constant. Right, and I had a much simpler implementation because I didn't need something that complex. Yeah, because I did a fall through so that I also did single strings. I don't know, basic Git, so using Git in a real project. Yeah, you can do some really cool things with Git, and as you can see, I make use of both, the diff logic that I have here and comparing what's over there, and we'll eventually start looking at the diff that we're getting from GitHub, because I really like the GitHub interface. GitHub makes it much clearer than what you usually see in just in a code editor. However, looking at this, I, for completeness sake, also implemented it that way, which I don't really care about. So I think here we still have that, so it's indeed commented out. I'm going to go for the new approach. However, he's defined a takey string constant, while I defined in my code over here a new token called tiki string. So obviously I'm going to have a look at where tiki string is used, because that probably needs to be changed to tiki constant. So we are actually going to keep our current change. We're going to keep this logic. My logic is less nice. This is actually checking for escapes and for extra double quotes. So definitely a nicer way of doing things. So yeah, we are going to make use of that. So I wonder why this was added. Actually, I wonder what PR added this in, because it's interesting that I'm not the only one who wanted to add the string information. So here we have some things where we're checking for string. Now I don't think we care about this, although again, one of the things that we should do first, and this is where this becomes really handy, that we that we can look at the changes that I've made before, and I can have a look over here, like what did I actually do with that. Now, unfortunately, that's the only thing I don't like, is that if there are divs that are too big, they will not be included right away, which means that I need to find out where I am using them by expanding things. So let's actually just start over here. Okay, so here's where I'm gonna, and here I've got TK string. That should actually now find it. There we go. 1. Okay, so this is where it starts getting important. 2. Yeah, so because I think all these we can ignore. We just purely need to look at here. So here we have the new code where it says, oh, that one. So he's using it here. Oh, for enums. So we've added enum support. Okay, cool. But it means that here we now need to make this string constant. Boom. And that gets us our shader template text. So let's double check if that is indeed going correct. So yeah, we can just get the text. Perfect. Now that also means that here we're introducing our string constant. Here we're introducing my string. We don't need that. We are just inserting the shader template entry here. I like adding things at the end of an enum so that all the existing enum values don't change. Although there is something to say for putting them near the other constants, but we don't have anything really that this belongs to. Maybe part of shader type. Okay, I am not going to try and pronounce your name, but I'm glad you're enjoying seeing me work on the custom shader template feature. It might, by the way, not be a final name. There has been some pushback on the name. So we'll see if someone comes up with a better name. I'm more than happy to change it. But yeah, right now it's called shader templates. To create my custom render scene buffers. You can. You need to do that through. I can't currently open up Godot, but if you actually, we can probably open up the whoops, nah, I'm not got focus on the wrong place. cbin Godot. So that's a previous one that we compiled. I don't want to do the console version, that's the normal version. Oh, of course it doesn't do that. Oh, nice. Imports. So I guess I just need to go and find the project that we had open a minute ago. Project. Where are you? Where are you? I can't see the wood for the trees here. Here we go. Compute. Shader. So yeah. Imports. So we're just opening up the project that we were looking at a minute ago with the last build that we did. It still work. And if we look at our code here, you can see that in our compositor effects, we get access to our render scene buffers object. And when we grab that, we can grab various objects. Now, somewhere, I think we're casting this. Or not. No, we're getting the standard ones. So if I go to here, that returns a scene render buffer object, which, am I looking at the right one? Okay, I don't actually cast it in our example. I should have cast it because what we're actually getting is a render scene buffers RD class. That one is only used for obviously the Vulkan renderers or the render device renderers. And that has a whole bunch of functions in here. So yes, it has that get color layer and all that sort of stuff that we are getting our existing buffers from. But it also has a create texture buffer command. Now this one's special. This one's different from the functions that you can do directly on the render device. Obviously, you can create your own buffers on the render device, but then you are responsible for the lifecycle of those. When you call this function with then, this is then something that you can choose yourself. The context is sort of like a grouping thing, so you could make a constant. You can make up your own word. You can make a constant for your game or whatever. It's just all those are sort of grouped together, so you can remove them in as a group. Then obviously you can give the thing a name. So that's you can my Pong buffer or something like that. You can give the data format, kind of important. Usage bits. Here you need to look into the render device what the usage bits are. They're very important because you're going to specify there whether you can read from them and write from them in the compute shader, whether they're used in raster shaders, etc. Obviously, how many samples do you want? So that's if you want MSAA, default is 1. That's the other thing. If you just specify a context and string name, all these should be getting default values based on what the standard color buffer is. So that way you create a texture. But the thing that is important here is that that texture doesn't just get created, it also gets cached. And it gets cached in such a way that if you call this every frame, it will only create the texture the first time. And the second time it's like, oh, I already have this one. I'm going to give you the texture that I already have. Until such time as there's a reason for Godot to delete your buffers, which happens, for instance, when your screen resizes, because now all the buffers that the scene buffers object manages are suddenly invalid because your screen is now bigger, and that means that that texture is gone. So there's some automatic cleanup there that you need to be aware of, but in 9 out of 10 situations, that actually helps in your advantage. Now, it is important that, yes, you can create additional buffers, which is really good if you want to do ping pong effects, for instance. But you can't then tell Godot to do its own built-in rendering into your buffers. So you can only use them as additional buffers. So for instance, if you want to do a 2-pass blur, you read from color, you write to your Pong buffer that you created. Then the next step, you read from your Pong buffer, you write back into Godot's color buffer. Boom, you have your 2-pass blur effect as a compositor effect. Or you can use this to remember the previous frame. So if you want to do like a motion blur effect, for instance, you can make a copy of your current frame as a compositor effect, and then next time around you can use that to do some blurring effect or that sort of stuff. So yeah, kind of important that that you can do those things. Now, one of the things that I would point you to, which I already discussed earlier today, is this example here. If you haven't looked at this example yet, so it's on my GitHub. Excuse me, RE radial sun rays. If you Google for that, you will probably find this. This is actually a multi-step composer effect, and this creates its own buffers to do stuff things. So yeah, you can create your own buffers and you can do things with it. So there you go. So let's close it back up. Let's go back here. So we've got that one finished now. So our TK string has gone there. It's no longer in those. So I'm happy with those 2 changes. That fixes that. However, the other things that we are dealing with are far more troublesome. Oh, I actually did change the mobile render. So as you can see here is it's already complaining about this. Now, it could be that this is the only thing that's changed because that's something that Dario mentioned to me. But yeah, this is the thing that I find very scary in doing this sort of work, because what I've done, as we talked about before, is I've actually stripped out things from the standard template and put them into includes so that you can reuse them. Now, one of the things that I did was I moved this into a new specialized constants include file, which you can now access from your own custom templates. So that is this little thing. However, it's changed. So, oops, where were we? Here. So I'm going to go and copy all this again. And I'm going to go and paste that in here, and I'm going to compare them and see what's different. So when we look at the toggles forward, there's still 0, 1, 2, 3. They're still 0, 1, 2, 3. So light projector, soft shadows. And actually, I'm going to go and delete my old ones, just in case that there's a spelling change. I don't think so. Hey, that's the story. I do want to make sure that the things are still the same and we don't have some weird, mismatch. I think there's just one new, the one that came in, and we can actually see that. We have this new one, use light map by cubic filter. That's a new constant in here. So that's probably all that's changed. So I'm actually kind of happy. We've got 13 instead of 12. So our include file is now actually that. Now has a new one. Thought I only saved, but yeah, I did save that one. So when we go over here, we actually want to do our incoming change. We do not want to keep that in there. Because we're now nicely including that, which is really cool. Sweet. That's hopefully all of that needs. Let's see what our mobile shader does. So obviously there are constant changes here as well. Interesting that we actually have the SE luminance multiplier here as a constant instead of a normal constant. I wonder why he's done that. But again, we're going to do the same thing. Oh, there's a couple of if defs in here. So we have some different things depending on the render mode. So let's go and have a look at these. So I did already do the mobile one. That's interesting. So I kind of want to see the same thing. What are we doing different here? So here we've got the SC is multi-mesh. That has disappeared. That I find slightly more worrisome, although I do remember that there were fixes around that. Okay, is that the only change? I think so. Okay. We still have things in there. Why would that be gone? All right, well, let's look at our current code in our source code. And just make sure that we're not about to do something dumb. So let's see, shaders. Mobile. I think we need to be in there. So this is where we have our spec constant. And okay, so yeah, that's over there. Let me guess, this is only in our fragment shade. No, that's in our. So it's still in there, but it's over here. So we moved it. So something else has changed because we only moved that in here. So what else has changed here? Ooh, that does look 0, 1, 2. Okay, let's do it like this and see. Use light projector, soft shadows. Okay, so that's the same. All right. We got these two. Because something has to have changed between ours and theirs. That's the same. That's the same. Okay. Where is our difference? Where is our difference? Has to be a difference. No. Unless it's something really dumb like they added a comment in or something. Actually, oh, this is only that one that's there. Hold on, right. Oh, that's for clusters. No. Here. Oh, that's in the fragment shader. Okay, let's go and look at the fragment shader. Fragment. Oh yeah, here. Boom, boom. Because I changed that to an include. Because it wouldn't worry me unless something has changed here. Okay, what else do we have here? Where were we? Oh, hold on. We did that one, we did that one. Oh yeah, we just checked those two from there. So the next one, 8. We didn't have a 7, we went straight to 8 here. I think we're now looking at our differences. Oh, sorry, I'm I'm looking at the wrong place. Okay, I got scared there. So that one's there. Okay, I'm actually happy with that. Okay, but now we have 9, 10, 11, 12, and we have 18. There we go. Boom. Now, one of the things that's important here is that we can see that there's a difference in implementation between the vertex shader and the fragment shader. In the vertex shader, we're only including our multi-mesh constant, while in the fragment shader, we were including everything else. Now, this is a global thing, or global to that shader. So we are now adding them all into a single include file that we're including both in the fragment shader and in the vertex shader. Which is fine. You know, if they don't get used in the vertex shader, they don't get ignored, as long as the constant IDs of them of these constants are the same over both shaders. So that is why we can actually do this. So we did that. These 4 are still all the same, so that's cool. We can get rid of all this, and then we can see that our luminance is in there, and now we have our. So my change is adding the is multi-mesh in both places, and the other person's change has been this one. So again, it's very important that we compare these, or else we might lose someone's changes. So kind of important. So with that done, we are happy with that. So we can go over here, and we actually can accept the incoming change because we want to have that in there. Very cool. Now, our last change over here is a little bit of multi-view. Ooh, this is going to be important because I moved that quite a bit. Ooh. Okay. Let's see. Okay, so the thing is that code has been added, this texture block by cubic. And what I've done is I actually moved that into a different place. But I also need to have a look at what do these things do. So yeah, but Elmade, remember that that is part of that PR that I've done. So without that PR, that code doesn't work unless, of course, you manually copy that struct in. But yeah, so be careful with that. So you can make it work, but not the way that I did it. You can't use the include file. You have to copy and paste that code in there. Well, the thing is, you lose that information, right? Once you render things to screen, all you have is an image. You don't know what the individual bits on that image are. That information is lost. So you do have renderers that render that sort of information to a separate output. And in theory, with the custom shader templates, it's something that you could add in. You could create another buffer, include that in, and then have access to that, and write that layer out to those. But yeah, standard, it doesn't do that. It's because it's a lot of overhead that you don't really want unless you really need something like that. But there's a whole bunch of things that you have to take into account that you actually you have to stay within the limits of what you can store in a texture. All right, so this is all new. But why does it do this whole block? That's the thing that I wonder about. All right, let me go and have a look in the changes here, what we're doing with use multi-view. So, okay, that is for mobile. So here we have if divide use views. Oh yeah, because we only had a little bit of information in here and I've got the whole block in there. Is that this part? Or is this what we have somewhere else? So this is what we have later on in the source code. That's a forward clustered one. It's still as forward clustered. Here's our mobile. So here we can see what we're doing. So I'm taking that whole block out because I'm moving that somewhere else. Is that indeed this thing? It is, because here we can see our, oh, these are two blocks. So this is the first block. I probably do the same thing later on. Yeah, here we go. So because this is all moved into, I'll quickly show that. I think it's an input attributes. Is it? No, it's not. Maybe in standard. Yeah, it's in standard ink. So that's all moved over here. And that's now in our standard include file that we include in both vertex and fragment shader. So that's all gone, which is why that shouldn't be in here. And the big question is, why, if I'm only removing this, why is it having a problem with the defines to keep compatibility with vertex? That is in here, even though, yeah, that's how I use multi-view. That's how we bring that in. Okay. Well, let's go and have a look here. So here we have a light map. Why is it having that problem? Oh my goodness. I am stumped because I don't see a reason why it would fall over this. So is there anything in this code that has changed? Multi-view, view index. Hey, Matthew. And it might just be a fluke because these two blocks are right next to each other and therefore the merge is getting confused. But I would have expected... Oh, hold on. This is, of course, the old code. I need to compare it with what we're doing over... No, what we... Yeah, no, I am comparing the right thing. I don't see anything that's changed in here that would explain why it's having a hissy fit. But I think all that we need to do right now is take that out. And then that code is all new. So we do accept current change, use light map. And then the only thing that I'm wondering about is if we shouldn't also move this into our standard include or into our input attributes. I'm not sure. For that, I need to have a look at where this is used. So it's in all three, and it's in our light functions. This looks correct as far as where it's included. Seeing that we haven't actually moved our light code anywhere, I'm happy to keep this in here. I don't see that as much of a problem. No, I don't think that's a problem. That's something that's for later cleanup. Because one of the things that we do want to do, as I mentioned before, is extract much more logic out of the main shaders into these include files so that you can include them into your own shader templates. And you can just pick and choose what you want to use instead of having to rebuild a whole bunch of this stuff. But it needs to be into logical little subsections. So yeah, that's something that we're going to have to deal with. But I think with that we have our changes. Now we might still have some things that didn't go right, but I think that we've got everything that we need. So we should not have any more of those. Just the default conflict marker. That's just a helper bit of text, so we can ignore that. So I think with that, we still. That's because that. So I need to go back to that one. So with that, I think we've got the changes that we need to do. So let's go and add those in. And then we can say git cherry pick, continue. And with that, we haven't really rebased it. We have updated it. So with that, that's it. Now, before I push that in, because I'm not going to do that right away, we need to go and test this. In order to test this, we are going to go back here, and we're not going to use you. We are going to use our test custom shader templates. That's the one that I was making a stream or two ago. No, last stream that was. So let's compile. That'll take a minute or two. Waiting for pre-launch build. Yeah. It takes a while. Why is it popping that up? That makes no sense. VS Code, you're drunk. Or is that just so that I can cancel it in between instead of doing something weird? I guess that would be a nice new feature. Why is Skype even running? With cursor, coding could be 30 times faster. How do you mean, Matthew? Oh, okay. Oh, of course. My cat's lying under my table and she's looking up at me like, what are you doing? Hello. Little pussycat. It's AI powered, all right. Yeah. I've got mixed feelings about AI when it comes to coding. I do have to say that I've seen 1 or 2 AI implementations that I thought were really cool, because they scan your existing code base and they learn from your existing code base, and then it's personal to you, and it makes suggestions on coding suggestions as you code based on your existing coding style. I kind of like that. And that I don't really see. I haven't really seen really good coding assists that do a better job than just auto completion and all of that. Well, I hope that Godot 5 is still a year or 3 away at this point. We just released Godot 4. Okay, that's interesting. So it saves the editor size on the project. And now that we open up a new project, I've got a full screen editor again. Yay! But we resize it once, and we should be good. Oh, and of course, let's change my layout. Yay! Alrighty, here we go. We now have a couple of boxes. If I remember correctly, oh, what's this error? Why is it complaining about that? It has nothing to do with this project. Sometimes Godot does weird things. Maybe I copied something across and it now thinks that there's something else that it should be accessing. Anyway, so let's have a look. No. Little tab key lots instead of writing is Quake 3. Okay. Yeah. Right now, if you ask me, having good coding skills is much more useful than anything else. So this is a normal material. So that's that box here. However, what you can see is on the material, there is now a new property called shader template that is pointing to my test shader template, and that is rendering this nice little block. And I think last time, not even show it. Oh yeah, so we can see that actually that test doesn't even have any coloration. It's just an unshaded box, and that is because that test shader template doesn't have any logic in it. Now, our second cube is actually a normal shader material, but that shader material, which is l.n shader, has got this keyword shader template in there, which is going to our l.n GD template. That was the one that I was building on my previous stream. And all that currently does is a standard l.n lighting model for direct lights only, which is, you see that there's a light shining here. That's actually this Omni light. This Omni light is affecting this cube, but it's not affecting this cube because I don't have that code in my shader template, and therefore it doesn't do anything. But this guy is the only one that's using Godot's built-in shader, I think. It is using a stock standard material, and it's not overriding the shader template. So this is Godot's stock shader that we're using here. So with that, we have proven that our PR still works. It compiles, it still does what it needs to do. Hopefully it hasn't broken anything that we're not testing here. But as far as the PR is concerned, I think we're pretty much in the clear. Obviously, as far as our l.n GD template, that one still needs a lot of work, which I did promise to do it on a stream about. I don't think we have enough time tonight, because like I said at the beginning of my stream, I need to wake up real early tomorrow. So I'm not going to make it much longer, but we are going to pick that up next time. We're just going to round off this PR first. And I will, I'll do a recap of how far we've gotten with shader templates before we end today's stream. Because also for myself, I would like to have a refresher and sort of go like, okay, What was I doing and where was I? We can see that our cubes, both cubes, still cast shadows, and that is because these both still have shadow versions of the shader. And of course, the shadow version of each shader is really simple. As long as it knows where the object is, it will write to the shadow map. So they are still casting shadow. Now I do believe that neither has got any shadow logic itself. So this block still casting shadows on our ground. That's also a normal material, but not casting shadows on our template shader because we haven't implemented shadow logic in our shaders. And that's really part of this whole thing. Let's park that. Actually, we'll talk a little bit more about it after we have done our last little bit of work here. Let's just save and close. That's fine. Because I want to make sure that we go. Oops. I need to go. No, I don't do that. I want to go and push this in. Alrighty. Boom. So we now need to refresh this. Oh, yeah, because that commit doesn't exist anymore, dude. So if we go back to this, we can now see that we're back on this one. So let's double check if that is indeed the correct one. And we should be able to see that because we have our extra bit of code in there. Very cool. And if we go to our other one, I think the best way to check whether we have everything that we expect is by having a look at, no, not those guys, these guys. So yeah, we're moving that. Oh, that's our standard one. That's all cool. That's fine. That's fine. There we go. So here we have our light map by cubic filter in there. That one into there. Okay, and then we should have a similar thing here. Yep, where we have both our multi-mesh and we have our bicubic filter in there. Sweet, perfect. Excuse me. So I think that is pretty much what I expect. I don't see any weird things in here. So I think we're in a pretty good shape here. Now, I do want to go back to, and I think that I'm mentioning the PR here, which is this one. It's the one that we checked in before. I just wanted to check whether these are all green ticks. They are. That's a final test, so we might just keep that open if we want to go and have a look at that later on, just to make sure they're all green. Because obviously if that's like a simple coding style check that I've missed, we could have fixed that up right away while we're here. Would have mean, again, cherry picking and everything, but that should now have been a lot easier. So for this one, we can see that all the main to-dos are done. Mentioned here that I want to do a separate PR for doing compatibility render at some point in time. And there's a bunch of additional things that we can do. We now just have stub logic in the other shaders. We could at some point do the same thing for sky shaders, for canvas, etc., allowing us to overrule a lot of inbuilt logic. We're also here in this PR going to our test custom shader templates project. That's a project that we're just running and looking at. And oh yeah, I've got a link to my previous stream where I build that guy and you can follow along with everything. Other than that, when we look at this, there's some questions that I think I've already answered. Just a guy sort of wondering, can we do something like a default for our main viewport? Might be something that we want to look at. Yeah, actually, remark that I do want to add that in at some point, but not tonight. So here I've got some more information about what I'm doing. That's still an outstanding question that I hope someone will at some point answer. That's still a question for Clay John to discuss with him at some point. These were my last changes that I've actually added the ability to to have both a 4+ and a mobile version of the code if you want to have that in there. So he still wanted to have an error, so that's something that I need to look at. Oh, what did I do? And then indeed, Callan now mentioned that he wasn't really happy about the GD template, so that's something that I think we need some more discussion about on what the naming should be. Yeah, I do agree that I need to find out, okay, how can I make this error? Say like, hey, I don't know what that is. I could probably do that in that that little bit of code that we edited before. Shadow time and shader template. Oh yeah, that's something that I still need to have a look at as well. So yeah, and again, I don't really want to do that tonight because I'm getting tired. So I think we're going to have a follow-up stream at some point where we deal with a few of these remarks instead of because this was actually I think this is actually something that I put in but didn't really finish, because one of the things that I've done here is I put a shader type at the top of our template code so that you can't accidentally use like a sky template with a spatial shader or something like that. So there's a check that those need to match, and that's probably where this is going wrong, because when it reloads that, it's probably losing some data. And I need to have another look at that, see what that's coming from. That should be correct. The only thing is that he's done that over here, which is weird because that is only a special mode that's normally not used, because normally that's the output. So 323. Okay, so that's an old message before. Oh no, he's got it over here too. Oh, because I've got both the mobile version and the normal version in here. But still, he's changing that here, which is really weird, because that's not used in normal conditions. That's only, I think this is only used when you're baking light maps. The actual output is this one. But even then, why does it give an error? It would have been nice to know what the actual error is, because at face value, that looks correct. That should zero out the green and the blue, and we should only be left with red. That should be a pretty, pretty easy way to verify that this is working the way it is. We could probably just have some fun with this and see if we can. Let's quickly see if we can actually reproduce that one. So, is this still in my? No, it's not. So bear with me for a second. Where are you? Probably tests. Test, and then. Okay, so I've opened up my Godot project here, and I did that a little bit too quickly because I should have started Godot first. We'll just start that up through just the command line just as easily. Or sorry, through the Explorer. So let me just find where we were. No, not the D drive. The C drive. Projects. Godot bin. Let's go and start Godot. And luckily it's still at the top. Okay, so we're back in that project. So right now I've got way too many things open. So I've got that project open in VS Code, and the reason that I've got it open in VS Code is when we look at our L.N GD template, which is the shader that we're mucking about with, we can't edit that yet in Godot itself. So if you try and open up that file in Godot, then Godot sort of says, "¿Qué pasa? I don't know what this file is." And that's probably not even going to be in version 1. You know, making these shader things editable, that is a thing for later. So right now you just need to edit them in a text editor. Now he was testing around with a test template, so we could probably, so this test GD template is the one that is being used to render this little block, and then the L.N template is used to render that little block. So let's look at the test one first. So this is the most basic version. So we have our we first defined that it's a spatial template. It can only be used for spatial shaders. We then say, well, here's the code for the for plus renderer. Then we say, you know, here's the vertex code for the plus renderer. And you can now see that well, there's some things that are very similar to what's in our Godot built-in template. It's just that we're using the simplified names here, the names with which these are known within Godot. We do have some outputs of fragment shader. So these are the things that we are calculating in our function and outputting to the fragment shader. Those are obviously not something that we're doing with include files because that's specific to what we're doing. Obviously, we have our GL position. That's our built-in variable that we need to declare. Here's just a little handy thing that we can access our time with global time. Not really using that at this point in time. Some of these are important because we need to expose those so that you can insert user stuff. And then there's a whole bunch of boilerplate code that you need to do. And some of this might even already be outdated because we did do some changes to multi-mesh, for instance. Yeah, I don't really want to look at that right now. That is something that we do need to handle when we really got times to properly polish this up. Can we set output for a custom render scene buffer? Not yet. That is definitely something that I want to add into this. Right now, you only have, and it's actually, when we look down here to the fragment shader, so here we define our fragment shader, you can see that we are including our output buffers. And that is, again, one of those, it's a shame that I don't have the other window open anymore. But that is, actually, I can probably, the easiest way to do that is actually go and look over here, of course. So if we go into files changed, and then we can go down to one of these. That's the, no, that's actually, I don't want that. These are output buffers. So these are all the default outputs of Godot. So at some point, I do want to make it possible that you can define an extra location output. And you can say like, hey, I actually have, you know, another output here, and that you can bind that in so that you can indeed do things like that. That's not in the current design yet, because these outputs are all hard-coded in the render pipelines that we create. But it is definitely something that I want to make possible, and that I think should be possible in the way that that this works. It's just that we need to do some interesting little bit of trickery for that. So, yeah, definitely something that I do want to make possible. Output buffers is defined here on the fragment shader. Do we also? Yeah, we got the mobile version as well. So you can see that there's quite a bit of boilerplate code still in here just to even do the simple fragment shader. And it's mostly just because without some of these things, you get errors. And that's, again, stuff that I do want to do more through include files. You know, a lot of these things, for instance, we are defining all these, even though none of these are used, we're defining them because else our shader compiler just, you know, so it's expecting all those. But the most important things are things like this, where you see hash code, fragment, that's where we're inserting our fragment shader. But in this case, we can see, or our user fragment code. And then in Godot, normally you then loop through your lights and then you insert your light code. Now in this case, you can see that there's a false block around there. We're actually not using our light code in this. We're not even doing any sort of lighting in here. Other than, do we do some sort of, no, you're just doing normal calculation here. So yeah, no, there's absolutely no lighting code in here. So that is the reason why in here our cube, even though our lighting is on and we don't have any sort of render mode. Oh yeah, the render modes are pretty much mostly ignored as well. Unless you implement that in your template. But why this cube is unshaded. So when we then look at our L.N GD shader, we can see that we have a much more elaborate implementation. I think our vertex shader is pretty much still the same. So again, there's a lot of boilerplate code that eventually should be handled by an include. If you just want to reuse most of that code, although it can still be useful to write it out yourself and do a very minimalistic implementation for performance reasons. This unpacking is very important. I explained it all in my previous stream where we built this from scratch. But the unpacking of vertex attributes, we actually we pack our vertex information so that we need to send less data over into GPU memory and handle less data in GPU memory. There's actually less performance impact in unpacking that data into variables than actually pushing data around in memory. So there's a little optimization there that you need to reproduce in your own version. Again, here we can see here's the user shader code. So that's a little bit of shader code that you write in your shader. So when we go look over here in our L.N shader, that line of code gets inserted over here. Kind of cool. It's get modified slightly, but that's basically what it does. And then here is our final output where we're outputting some of our variables between our vertex shader and our fragment shader. And obviously the most important thing is our GL position. Without our GL position, nothing gets rendered. But then on a fragment shader, we do a little bit more. So we still have that same amount of boilerplate. Here's our inputs, our inputs that match the outputs of our vertex shader. This one belongs to that as well. We again have our global time thingy. And then here's our main where we do a bunch of setup. We're actually assigning more things here because we're doing more of the lighting code. Although we mostly have the same stuff here. Again, we insert our fragment code, but then here is where stuff starts to change. I handle some of the ambient light here. So if we're not using a light map, and again, if we do use a light map, I'm missing the implementation, so light maps don't work in this shader. But if we do not use a light map, then I'm at least parsing my ambient light. And the ambient light information is stored in our scene data. Again, the thing that we handled earlier in the stream. So we're getting both whether it's enabled and we're getting the actual color light of the ambient light. And we're storing that for later use. Then for some reason, oh yeah, if we then have an ambient light disabled instead of just not running that code, we're setting it back to 0. Again, I've just copied this out of the existing implementation. And I think that the shader compiler will optimize this out. See that we override this here, that what we're doing here is completely useless and it'll chuck it out. Assuming that light disabled is enabled. We could have just gone and make that part of the if defs here. But if we do have it, we're actually going to go and multiply our ambient light with our albedo and with our AO, which is our ambient occlusion. I had to think of that word. But in this case, our ambient occlusion is always 1. So it just stays the same. But if we were to obtain our ambient, actually that's true. That is actually something that could potentially be said in our fragment shader. So for that part, our ambient occlusion will actually work. But we're not reading our ambient occlusion in any other way. But if you have it in a texture, and you're reading that in the fragment shader, ambient occlusion will work in this shader. But the most important thing is, which we are missing in the other one, besides the ambient light, is that we're doing a diffuse light calculation here. And what we're doing is we're looping through our direct lights. Interestingly, we are in our so I guess for our mobile renderer and our 4 plus renderer, we have a maximum of 8 directional lights. That's interesting. But we look through those potential lights. There's an early breakout if we are past the number of actual directional lights that we have. Now, why we're not just putting this in here is a very strange optimization. It has everything to do that when we have a fixed number in here, 8, our shader compiler is actually more equipped in optimizing this than if we put this in there and our shader compiler doesn't know the maximum number of times this loop goes through. It will actually make worse code than if you do it this way. So strangely enough, this is more performance, which is something I didn't know until that was explained to me. One of the things that I think would be interesting to try at some point in time, but it's something that I definitely want to do on the mobile renderer, is turn that into a specialization constant, where you actually can compile different versions of the shader depending on the number of lights that are active, because that would actually result in even faster shader code, especially if you have a limited number of lights. Let's say that you only have one directional light and one spotlight. Whammo, you get a much more efficient shader code. And that's actually one of the things that I have been wondering about here as well, as something for an optimization for myself when I look at creating my own template, is I, for instance, would like to make a template that just only supports one directional light. 9 out of 10 games only have one directional light. Why loop through 8? And on a modern GPU, this will be efficient, but on an older GPU that doesn't have the best optimizations around this, there might actually be more overhead in cycling through those 8 lights and figuring out that only one is used. Yeah, there's an interesting balance there. So I actually believe that, for instance, for mobile VR, it might actually be smart to just support a single directional light. Have that in here, just have a switch here. In that case, it would actually be around an if-def. If the directional lights are there, go and run them. If they're not there, I'm actually surprised that we don't have a shader constant. Maybe that's something that I forgot to put in here. That's a good one. Okay, I'm getting curious. That means I need to go here. I need to go here. And I know that this is the old code, but let's go back into our clustered server. We go into here and we go, let's go find that. So here we're looping through, that's full code. That's not what I'm after. Here we go. So directional light, not unshaded. I guess there isn't a constant for that. I thought there was. Maybe that's only in the mobile renderer then. Yeah, in the mobile renderer, we actually have a constant for that. So I am going to go and check if I was smart enough. Is there a mobile version in here? No, this doesn't even have a mobile version. I'm actually going to go for myself. But that's actually interesting that we are not excluding that code. It's actually something that I'm going to talk to Clay about, because it's interesting that we don't just kick that out. I get when it's unshaded. You know, I guess it's not very likely that you will not have any directional lights if you are using shading, but I'm actually very surprised that we are only doing that on the mobile renderer, because that is a really decent optimization. Anyway, as we can see, even in the mobile renderer, there's a whole lot of things that we're doing. Now, most of this is shadow code, but even in the lighting code, that's done somewhere here. Oh, this is only for the shadow thing, so probably Oh yeah, so here we're actually doing lights. So that was only for the shadow mapping. And then here we're actually doing the actual lighting code, which is quite complex, especially when we are looking at the fact that we are... No, I'm still in the wrong place. Here we go. Yeah, this is where we're calling the light compute. So we actually have a separate function called light compute that then calculates the light value for this light and does something like that. But I've got a much simpler implementation here. This is old school what I'm doing here. This is the most simplest, basically the old font shading, I believe that that's called. Where all we're doing is we're taking the color of this light. So this is a big array that we've got access to in our shader. And you know, with our index, so we're getting our light index. Yeah, because the directional lights we just have 8 that we just get access to. So yeah, we're just checking the mask and then we're applying it. So boom, here we go. Hello, we've got a light, we got some energy, we got some direction. And it's actually the direction that's important. So what we're doing is and that's what the L.n comes from. L from light, dot is the dot matrix or dot product function. And we're doing that with n, a normal. Simple. Light's coming from that direction. The normal of my surface is that direction. And the angle between that, the bigger the angle, the less light is on that object. It's the simplest lighting that's possible. It's, you know, it's not spectacular, but for simple lighting, it works, right? It's just, you know, here we can see that the normal faces away from the sun is there, so we face away. If whenever that angle is more than 90 degrees, then hello, we're in the dark. And if that angle is, you know, in this case, it's not direct, so the light's coming from there, and our normal is there, so this is maybe like a 22-degree angle, and that means that, you know, we get the lights adjusted accordingly. You'll see that if we actually rotate, no, not the thing. I want to rotate my cube. You see that it gets darker the further away from the light we get. So that's all that does. Simple as that. So here we simply multiply our albedo by the color of our light, by our light energy version. So even these two for a white light you could even do without. And then times that L.n that we're doing here, and that gives our diffuse light. And then later on, when we go and do some final checks here, the main output is over here, which is our frag color. And we just add the ambient light that we calculated with our diffuse light that we calculated. And that's our light output. That's all that we're doing here. And then with that, we have a really, 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 really simple bit of lighting code. And again, this is the other thing that's important. This works for a forward clustered renderer. If we would do the same for our mobile renderer, where's our thing? So in our mobile renderer, let's go back to where our directional light is defined. You can see that it's kind of the same in the beginning. I think for directional lights, it will actually be very similar. It is for positional lights that actually things change. So when we look at omni lights, we're actually using some indus data because we're in CPU defining which lights are affecting a certain surface, and we're then checking up to 8 lights, and we're doing that. However, on the clustered side, when we go past all of this and we go and look at our omni lights, we are checking our clustered buffer for that stuff. Now, one thing that's really interesting is our clustered code is not yet in an include file. So we actually need to go and copy that bit of code. let's do that for fun. This is actually a pretty fun exercise for just finishing off the night, I think. So we're going to, so that's our fragment shader. So we're going to go and copy in this bit of code. So that should move into an include file at some point. And this is stuff that handles our cluster data. You can see that it's actually getting information from our cluster buffer. Yee. Now our cluster buffer is, when we're looking at our forward plus renderer, what makes our forward plus renderer special and fast compared to our normal forward renderer. So our mobile renderer is a normal forward renderer with a maximum number of lights, and fairly inefficient because fairly inefficient on a large number of lights. So for the mobile render, it works pretty well with a limited number of lights. But if you have a lot of lights in your scene, you're going to get into trouble because the more lights you do in a standard forward plus renderer, in a standard forward renderer, the more problems you ran into because you're going to loop through all those lights every fragment that you do, whether they are important or not. So you get a different approach. And again, that's also where I think that there is a lot of optimization still possible in the mobile renderer. In the forward plus renderer, we are using what is called a cluster. And what that means is that before we render all our geometry, we are doing a pass. So we're actually first rendering all our depth buffer. So that's our depth pre-pass, where we render all the geometry that we have to the depth buffer. That has two advantages. One is we now have a depth buffer that we can use for a number of effects that need the depth buffer up front, including the clustering logic. But also it means that when we then do the actual rendering of the objects, we have a pre-filled in depth buffer, which means that we have a lot less overdraw. And obviously with overdraw, meaning that for a single fragment on the screen, you are rendering multiple objects because the order in which they are rendered, because right now we're not rendering sorted for very good reasons. It's possible that you have objects rendering that on that fragment, multiple objects being rendered on a fragment. And if you have very costly fragment shaders, which do very, next generation lighting, that's overhead. You only want to do that one time. With a depth pre-pass, you actually get to discard most of those fragments because now you know what the depth of the frontmost object is. And then when you're actually rendering the fragment shader for the actual lighting, for your actual objects, you can cast them all out and you don't get that overdraw overhead. So for the more complex scenes, that's actually a savior. But the other thing is, so we render to our depth buffer, and then we do our cluster logic. And what a cluster logic does is it actually renders the lights, but as not for lighting, but just for figuring out which fragments are affected by which light. So see for instance, an omni-light, which is basically a sphere with the radius of the sphere being how far the light can illuminate an object. So you render that sphere using that depth buffer that only where obviously that light, the distance between the light and the current depth of that pixel, if that distance is within the radius of the light, that means that light affects that pixel. And now you can create a cluster buffer, and the cluster buffer tells for every fragment on screen which lights affected. So you could have 1,000 lights in your scene. Let's say that you have a big city and you have all the street lights on your city. 1,000 street lights all there. But one street light is probably only going to affect the object, or is only going to affect the object near to you. So if a car is parked underneath a street light, only that light, that street light is going to illuminate that car. That car isn't going to be illuminated by, the other, 999 lights in your scene. Now, with a normal forward renderer, it would have to go through all 1,000 to figure out. Now, in this case, you in your cluster buffer, you know that for that fragment, only that street light, maybe the one next to it might at most be lit by 2 of the street lights. It will be in that cluster buffer, and therefore you only render the light for the 2 lights, and it's just as fast as a deferred renderer without all the overhead that the deferred renderer has. It's absolute magic. Clustering is super cool. However, the downside of clustering is it requires modern compute shader support. There are some sort of intermediate versions of clustering where you can do it completely with raster renderers and without compute. But if you really want to have it work properly, then you need compute shaders, and you need, you know, the really good ones, the GPUs that know how to properly do that stuff. And some older GPUs, they don't support the full compute shader functionality, which is a bit of an annoyance. But anyway, that's what makes the forward plus shader or renderer in Godot so cool. Again, you know, there are still a lot of optimizations that we can do, but as a forward renderer, the clustering is what makes it fast and what makes it really good, provided you have hardware that supports it properly. So let's see that in effect. So we somewhere, so in between the def pre-pass and the first opaque pass, there is a step that builds the cluster, and then we start using the cluster. So for our directional lights, they ignore that. That's why we're still looping through our 8 directional lights. However, for our for our Omni lights, we actually need to go and handle our cluster. Now you can see that decals are marked in the cluster, reflections are marked in the cluster, Omni lights are marked in the cluster, so that's what we're going to be looking at right now. And again, we are using the full functionality here, and I'm just going to copy all this because I don't want to, and I'm going to copy it up until here. I'm going to put that in there. Boom. So here we're going to do Omni lights. So this code is for forward plus only. And we'll explain what it does in a minute. Just need to go do this. Now, Omni lights and spotlights are currently still split in Godot. I actually believe that they should be together. Seacrest, no, this is replacing the built-in shader template logic that's in Godot itself, so that you can create your own base code, or it's not really the right word for it, but you can create your own lighting model inside Godot, and therefore deviate away from more complex lighting and save performance. Or, you know, one of the other use cases for this, once we complete all the include logic, that you can actually include all the existing bits of the Godot renderer, is that you could extend the templates, that you could just include every bit of code that's in the standard renderer. And then, for instance, for toon shaders, it's a good one, where you can just add code at the end of the fragment shader to better handle the toon logic, which is currently not possible in the normal sense of that. So, okay, we have our standard loop here for OmniLight. So this is the boilerplate code that we need for that. What is it doing? We get a cluster offset for the Omni offset. I'm not quite sure where that is coming from. Let's see. I wonder why that isn't, because indeed I need to go and make sure that this is included. So this is all the standard stuff as well. So obviously we need that somewhere at the start. Do I already have? Not yet. So here we're doing all our normal lighting code. So we're just going to go and put that over here just as a start. So we got a cluster position that we calculate here. I don't think I'm doing my combined UV yet. Or am I? No, I don't. So I'm missing that. That's kind of a bit of a hack, but let's go and put that in there. Which also means that I need my combined projected UV logic. Oh, we're opening a house of cards here. So yeah, so well, that's interesting. That needs to be okay. So we got all these. If we have multi-view, we want to have this one in there. We have 1, 2, 3, 4, 5, 6, 7, which means we also need to have that as an output here. So now we have an output vec for combined projected. Now we need to have the logic for combined projected. That's after GL position. Okay, that's cool. And we also need to combine projection. Where's that coming from? That's just in the use multi-view here. Where are we? Here we go. Cool. So this is actually something that I still need to improve, but which works a little bit as a fluke, which is kind of interesting. Because we're not doing the clustering per eye. We're doing the clustering on our combined projection and then reprojecting it to each individual eye. And that works good enough for what we need to do. But it is a bit of a fluke. So yeah, one of these days I still want to make sure that our clustering is actually being done per eye instead of doing separate. That's still one of the things that I still need to improve in the 4+ renderer. Anyway, we now have that logic. We're not doing anything with multi-view here. I'm just putting that in for completeness sake. For what we're doing right now, all that is important is that we get that cluster position. So this is basically looking inside of that cluster buffer. Where is our data for our lighting data for that fragment? So we get a position from that. And with some of the other information that we have. So, okay, that's coming from implementation data. That's the other thing that we need to reproduce. No, I think we're getting that in there, so that's all right. So we're getting all our cluster data in, we're getting our offset. This one's really important. We're getting our Z. So for our Z for our current vertex, do we have our minus? Do we have that information here? Yeah, so we're getting our interpolated vertex, perfect. So for our current vertex of our of the pixel that we're currently rendering, we're getting a value by Z far. So between 0 and 1, well, actually between 0 and 32. No, it's clamped to 31. Okay. We just get a normalized value between, you know, our near and our far. Where are we? Because all our cluster data is stored in there. So that's our cluster Z that we have here. So our offset is where in our cluster buffer is our fragment that we're currently rendering. And the Z is just, okay, what is the depth of our current pixel? Because again, we only want the lights that where the radius of the lights means that it can hit that fragment. And we need to know that by that Z cluster. In here, we start with a cluster offset. Now, I don't know why that isn't just added in there. Because when I looked at the code here, let's go and get the Omni offset here again. We can see that we're doing that here, but in the other places, for the other lights, so let's go in Spotlight, for instance. We're actually adding that in here immediately. The cluster type size, boom. Don't know why. Maybe because our Omni lights are at the beginning. That's the only thing I can think of. So yeah, we're starting this with our cluster offset there. That's fine. And then we are going to call that get items in range, which is going to check the cluster data and get information within our cluster data for all the lights that are within range. And it does that with, I guess, with ranges and an index. I haven't looked at the underlying implementation yet. I just know how it works in essence. Now here we're doing something really cool, which is that if we have subgroup support, we're actually going to use subgroups. What are subgroups? So subgroups are when you're looking at compute shaders, what we did before when we were working on our original include PR, we could see that you could run fragments in the compute shader. I shouldn't really call them fragments, but invocations of the compute shader in parallel. And you could give them a block. So we had an 8x8 block. All those compute shaders would be running in parallel, and they're called a group. And the nice thing about a group is that you can communicate with each other. You can put sync points in your compute shader where each invocation of the compute shader needs to go to that point, and only when they're all at that point, then you continue to the next bit, and you can therefore transfer data between them, or they can all write data into a buffer, and they all have access to the buffer, and they do some funky things with them, and it means that you can do some really cool things with parallelization. You have similar logic in raster shaders. So here we're obviously doing a raster shader, but if you have subgroup support, you can create some communication between those things. And that again means that we can make more efficient use of the cluster logic in this case, because they can use that same information. Because I believe that actually clustering information is not stored on the resolution of your buffer, but per tile. So you have the cluster of like a block of 16 by 16 fragments. So that's what we're doing here, is that if possible, we're adding some nice little helper things here that optimize this a bit. However, even if we don't have subgroups, what we're doing is we're looping through that list of items. So in our cluster data, starting from the first item until the last item, because they're sorted by depth. So we already checked against our depth value, excuse me, that we're only going to get the lights that could potentially get hit our fragment. So we're looping through those items in our list, and through a mask. And again, I don't know enough about the actual underlying implementation here, but we're getting that data back, and it's eventually going to end up giving us just the light indexes for those lights that we need to process that hit our that hit our fragment. So yeah, again, I don't know exactly tell how this works. I didn't write this, but eventually with that merge mask, if we have one, we know that actual lights that we are currently processing between what we found in the range is actually potentially lighting our fragment that we're doing right now. So if any of that fails, then we hit continue, and we just skip that light and we go to the next one. eventually we come here and we now have, yippee, we have a light that potentially lights our fragment. There's two more checks that we do. The first check is whether that light's layer matches our layer mask. So on every instance, you can say on which visual layers, excuse me, that that object is on, and we're only get lit by a light if we share visual layers. So if we don't, even though that light is in range, even though that light could potentially light our fragment, it's not set to light this object, and therefore we skip. And the other thing that we check is whether we are using the light map. If we are using light maps and we have marked this light as static, and I'm actually kind of surprised that static lights, if the light map is turned on, aren't just skipped and not added into the cluster. So that's something that I wouldn't mind having a look at. If maybe it actually does that, and this check is useless. Very possible. But we basically say, hey, if it's a static light and it's been baked into the light map, obviously we're not going to light it here because we're using the light map to light this. So that's what that check is. So now we've come here, we have our light index, we know which light is lighting this fragment. We now know that that it's not baked. We have a light that we need to process. Now in here we can see that it's simply calling a function called light process omni, and it is processing that. Now, if we're smart, I could move this little bit of code into my light process code, but I am, what you call it? I'm lazy. So I am just going to go and copy this over, and I'm going to paste it over here, and I'm going to indent that. Okay, and now I'm just going to change that to actually using the correct data. So I've got my light index. Cool. I need to find out. That is, of course, in one of my other functions. Light data inc, probably. So if I would have include, oh no, the light data inc is just getting me the light data. Where is forward lights inc? Why is that actually? I don't know. Okay, no. Yes. So here's our actual light code, and the reason why I want to have a look at that is I want to know where it's coming from. So OmniLight's data. So this is actually included through our light data here. So that's our light data structure. And then somewhere in here, no, we don't. Where is our? Okay. That also means we first need to check, are we including our light data in here? We should, because we're getting our directional light information from that. And that is because that is coming in from too many things to check. Oh, yes. Which one is it? No. Input. Here we go. Is it input? Actually, in our, which one's the standard include? Here's our standard include. Oh, because we already have a standard include, so that sucks. This is where I wish this was already merged so that we had one thing to look at, but we're already including our light data through our standard include. We have a bunch of that stuff, and then here we already have our OmniLights buffer set. So we already know that we're bringing that in. And I think I've moved some of this into the other include, but we know that we have that data coming in. That's really cool. So we now know that we have, where were we with this? So this now becomes OmniLight's data. And then obviously we want to do that with the light index. And then I bet you that we have a color version thing in there. So now we go back here to our light data include. And here's our light data. So we have a position of our light. We have a direction of our light. That's only important if it's a spotlight. But in our case, the position of the light is important. We got a size of the light, that is how far it is. So there's a couple of more things that we need to do here. We're actually going to cheat for now. but we obviously need to calculate a fall off. The further away from the light we are, the darker it must become. So there's a little bit more than our standard L dot N calculation that we need to do here. But we're going to cheat for a second just to get it started. But the thing is that what's important is we have a color. Perfect. Boom. Now we go on the lights, light index. Do we have an energy in here? I don't think, do lights have an energy, or is it pre-multiplied? I think it's pre. Ooh, we got a projector for spotlights. We definitely need to make sure that we have projectors. Although we won't do that tonight because it's nearly 12. I really need to go to bed. Anyway, I don't think we have an energy, so we're not going to do energy here. Which means that we're not going to do energy. Now, we do have a direction, but that one we need to calculate. So we're going to go, say light data, light index, direction is actually going to be the position of the light. Now, if I remember correctly, but I could be wrong, but if I remember correctly, the position of the light is pre-multiplied with our combined view matrix, which means that we can simply take this position and then subtract our vertex from that. And that gives our light direction. We might need to flip that around. It might be vertex minus position. I'm not quite sure, but we're going to go this way around. And then we have our normal L dot N. Now we need to still calculate a fall off. So I'm actually going to put a to do here. Calculate fall off depending on the distance. The other thing is that this light direction needs to be normalized. So I'm actually going to go and copy this and say light delta is that, because we want to use that later on. And then we want to do normalize light delta. There we go. Because for our L dot N, we need to use normalized vectors. Okay, so we got a color, we got our light direction, we have our L dot N. We do not have our fall off yet, so it's going to be bright no matter how far away we are from the light until we're at the, because that's what our clustering does. Our clustering already limits our the distance from to which our light can be affecting fragments. Because normally it would have that fall off. It would the light would go down to 0 by that point. Now we're getting the same light strength, and it's going to be looking really funny because, as I said, the clustering is actually working on tiles. So we're not doing it for every fragment. We're doing it for groups of fragments. So let's see if this actually reloads right away. I don't think so. It should. I'm not sure why it doesn't. Oh, so that one was still on light mode. That's funny. So either our logic is not working or our shader has not been reloaded. So let's just do reload current project just in case that helps. Maybe our shader doesn't compile anymore. That's also possible. There we go. Although I would have expected some errors. So, because I would now expect that this, because this is an only light, right? Yeah, it's an only light. So I would have expected that to actually do something with our cube. We're not getting any errors, so because that is our n.n shader, yep. And we did add this to our l.n template, yep. So we're still missing something in our cluster logic. Why, oh why? Now, one thing that we can do, Serge, I always leave my streams on YouTube. So yes, this stream will be forever available. Just for testing, I am just going to add full red to this because I just want to see if we are actually, yep. So we are going through that code. Sweet. All right, so now the question is, let's start with just doing this as 1.0. Okay, that's not doing anything. So we're either not getting the right light color. No, the albedo should work. Okay, let's take light color out and see if we... Oh yeah, we can... Actually, well, let me go and comment that out again. That we keep that. Let's give it just a hard code this to, we're going to add red to that. So yeah, we can see that the red's there, not on those because our n.nl doesn't work there. So, and if I now do albedo times that. Okay, I think my problem is because this light is purple. No, I don't think that matters. That should still be there. Why is... I think my problem is that because I'm making this completely red right now, but I'm multiplying it with the color of the texture. So I am wondering if there's no red in my texture, it's not going to show up. So one of the things that I can do is with this one, let's make sure there is plenty of color in there, just to rule that out. But I still am not seeing a big red amount. There is a difference if I turn that off and turn it on. So it's definitely doing something, but it's not doing what I'm expecting it to do. Because with this being purely red, I'm expecting it to become more red. With this light, do I have an energy on that light? I think that means that my color is actually pre-multiplied with that light. So it's also interesting. You can see that this doesn't really color red, and that is because there's no red in the green there. So that's interesting. So yeah, I think that the light intensity is actually pre-multiplied in this. But on our white cube, I would still expect to see purple. And I am not seeing purple. So what am I doing wrong? Because that is the albedo that we are calculating here. Also for my ambient lights. Unshaded, we're just getting albedo, that's fine. Yeah, the albedo is whatever we assign in our fragment color, so... let's just for fun go and take our normal light. So here we can see, oh, we're probably just getting... So it was working. It was actually working. But because we already have our directional light fully lighting our cube, which I've now turned off, we weren't seeing the effect. We're actually getting, we're topping out our light. We're getting too bright. And that's also part because of this energy that I put in. It actually means that we're going to we bloom out our light at that point in time. So we can actually see that it is actually doing the right thing. The only thing that it's doing wrong right now is, we can go and see that when we move this out towards, that's what I was seeing, what we're waiting for. So what you can see is that now we're hitting the border at which that light should have an effect. And we are not doing any fall off calculation at this point in time. And here you can see those clusters. So one cell in the cluster data is holding cluster data for that entire tile. And you can see that therefore we get these blocks that are cut out because that tile is still including that light because of the range of that light is just about hitting that tile, but it's no longer hitting those tiles. And if I probably move that a little bit more like that, yeah, you can see there's the border of our circle. So here we can very effectively see how our cluster data is making sure that we're only processing this light if this light is actually hitting our cube. The mistake that we're doing is because we're not calculating fall off, we're still fully lighting it over here, and we would have still been fully lighting it all the way over there, but our cluster data is stopping our light over there. It's saying anything beyond the radius of the light, where the light no longer has strength to light our surface, that's where we're stopping lighting those things. So that's a really interesting way to see the clustering logic take effect. And that was also where I was getting a little bit confused by some of the code because it's tile, because we're not doing it for every fragment, we're doing it for every block of fragments. So the cluster is actually rendered at a lower resolution. Well, it's not really rendered because it's a compute shader and it's data. We're basically getting a range of lights within the Z depth that would apply. However, that applied to the whole little block. And that is why we have the extra logic here to say, let's bring that down to what is actually affecting our light still. So to complete things, we now need to do something with the fall off. I'm going to leave this commented out for a minute, or, actually what we could do is we could turn it back on. So now it becomes way too white. But what we're instead going to do is we're going to go to our directional light here, and we're just going to make that a lot lower. Because again, the reason why this wasn't working was that our cube was already fully lit, and then we hit the maximum lighting value and we no longer get an effect. If we would have done auto exposure, we might have brought that red balance back into view. So let's work on fall off, and that is going to be a little bit more tricky because I don't remember off the top of my head the fall off calculation. But what we need to do is, now that we have our light delta here, is we need to calculate a distance, which is light delta. We need to get the length of that. And now if we're smart, because we are calculating the length, and that is the what you call it? I'm thinking of, that is a costly part of this calculation. Might as well just do a divide. And I don't really know if that is important with shaders, or if shaders are optimized there. Actually, we do want to go and do a zero check so that we don't get a divide by zero. And then obviously we actually want that defined separately. And that becomes effect 3, 0. Which will screw up our dot m then becomes 0, and we don't get lighting, I think. So now we need to get that out of there. So now we have that, but now we have a distance that we can use. And that I am going to steal from the code in Godot, because I don't know that off the top of my head what is the best way to do that. So, and again, I'm taking some shortcuts here because we are doing way more logic here. I think it's actually our get omni attenuation. So that's our line length. We got that as distance. Radius attenuation. Okay, let's go and put that in. We're going to copy that and then I'm going to find that function. Let's use the same names, but we're going to go and copy that and copy that. Perfect. And now obviously we need to get that attenuation function. There we go. And we're just going to put that right next to our... And again, normally we would actually want to include that from the Godot logic, but we are just going to go and get it like that. So now we have an attenuation, which should be a value between 0 and 1, I believe, which means that we can just add that to our series of calculations here. Ooh, we got an error. All right, so what is the error? Yeah, that's not very helpful, because that's way too big an error. But we know that it's something in our new little bit of code. That's just a comment. We are doing... Oh, can I look at my code, please? Thank you. So your light length. Yep. Okay. Yeah, that should be good. What are we missing here? What are we not doing right? Okay, let's start by commenting out a few things and see at what points. No, that's still erroring out. What am I doing wrong? My delta is dot dot dot. Okay, how about go away with... I hate these stupid pop-ups. They take way too much room. Anyway, just wait until they're gone. There we go, they're gone. Okay, let's see if it's left enough in here for us to use. Distance. We still have the distance in there. Boom. Nope, not light direction. Light length. Very good. Thank you, Baz. All right, so let's go and undo that and see if it works this time. Boom. This time it's happy. We see that it's no longer... Our light is no longer applied here because it's now dark. And now if we move the light closer, we slowly see the light affecting. Da-da-da! Perfect. So we are now seeing that our light calculation is working. Again, a way more simpler lighting model than the standard lighting model in Godot. So we lost all our PBR functionality and all the other cool stuff, but we have a spotlight that right now affects our cube. And we now have an example of how our cluster data works and how we get data from our cluster data. And now it's basically a matter of repeating the same for spotlights and decals and all that sort of jazz. Again, I am very surprised that there isn't... Well, no, actually, I'm not surprised because we wouldn't know that on an object-by-object basis. So that's why it's always looping through the cluster data. The other thing that I really think... Well, that's something that I really need to discuss with Clay at some point in time, is one of the optimizations that we saw that one of the other engines does is that they've removed the difference between omnilights and spotlights. Basically, omnilights and spotlights are just treated as lights, and the only difference is that the light angle is 180 degrees, or because it goes both ways, right? So basically, it's 360 degrees for an omnilight, and that means that you you have a much simpler lookup of lights. You don't have the two loops, you just have the one loop, and it just works. And it's just one extra line of code for that angle check, and simple as that. What do you think is the best way to contribute if you don't understand C++ code? That depends on what your definition of contributing is. In our definition, there are many ways that you can contribute to Godot that has nothing to do with coding C++. One good way is just helping us find problems and raising issues on GitHub and saying, hey, I have an example library here, or an example project here that clearly shows a problem in Godot. Can you go fix it? Another way that a lot of people contribute that we really encourage is helping out with the documentation. So if you spend a lot of time figuring out how multi-meshes work, and you go to the help pages in Godot, you sort of go like, I can do a better job at describing this. Write an help page over multi-meshes or any other subject in Godot where you can obviously write about that sort of stuff. So, and I think we even have a nice page for that as well. So if you go to godotengine.org and you go into contribute and say how to contribute. Obviously, we want money. We need to survive somehow. But you can, like I said, help by raising bugs and suggestions. You can help. This one is really important because not enough people do it. But in the development cycle of Godot, we will release dev builds, and especially right now, Godot 4.3 has been released. We've just done our first 4.4 dev build. That's probably going to be a fairly unstable dev build because we merged a whole bunch of new stuff in there. The more people who are willing to help out, test those dev versions and see if there's regressions or things don't work properly, the better Godot goes. So that's a way that you can contribute. You can contribute by, C++. So that's the one that you were sort of going like, that's really not something that I'm good at. You can help with reviewing other people's work. Again, that does require some more knowledge of C++, but looking at your thing that you are a .NET developer, so I'm assuming that you know some of the other dialects, maybe you know C#. Well, C++ isn't that far removed. So you could probably look at other people's PRs and sort of try and understand what they're doing. And when you do know how a technique works, but you just don't know the dialect that is being used as far as the coding style is concerned, you can still get to a point where you might be able to figure out, okay, I can do something with that. Writing plugins, that's something that a lot of people do as well, and you can write plugins in GDScript. Or if you are .NET, assuming that you are, you do understand C#, there are a lot of people who like using C# with Godot, and that's still unfortunately underrepresented in our community. So there's a lot of things that you can help out there, writing plugins in C# to help people along. On the documentation side, actually documentation is mentioned over here, but there's many places where we only have GDScript examples, so converting those to C# examples, that's ways to help out. So yeah, so there's a whole bunch of helping out with the community is always appreciated. So there's plenty of ways that you can help out without knowing C++. L8M, off-topic question on Radial Sunrays project. Demo scene has a lot of visual jitter over time. Compositor edge detection, testing Sobel and difference of Gaussians amplifies this a lot in a bad way. Yes, you got to understand with the Radial Sunrays is that that is something that I wrote fairly straightforward based on an example by someone else. So obviously I haven't gone through all the edge cases and seeing how it works long term. It was meant as an example of how to use compositor effects and how to approach certain things. So I'm pretty sure that there is a lot of improvement to be done on that one. And for that, it's kind of the same thing as that I just mentioned to Seacrest. Is anybody willing to go through it and make suggestions for improvements or raise PRs on that. More to the scene itself. Yeah, I'm not an artist. I just grabbed something from what you call it, from Sketchfab, and just put it in there, and that's where I went for. If it's turned off, that might be something to do with one of the latest changes, that it was accidentally turned off. That is very possible. I'm actually surprised about that, but it is definitely possible. I would have to try it out myself and see if something's changed in 4.4. But yeah, or maybe I checked in something wrong. That's very possible. Alrighty, it is past midnight for me. I have to be up in about 6 hours. So I think that I'm going to leave it there, everybody. I hope this was interesting. I hope people enjoyed following along. You got to see a little bit of behind the scenes work on how we prepare PRs and how we rebase PRs, or at least how I do it. We looked a little bit at the internals of the shader template logic that's coming along. Now I'm hoping, speaking of contributing, people testing out my PRs is a great way of contributing to the engine. See if it works for you. See if you can find issues with it. Actually, before we finish, I will go and no, it's not here. It is tests. No, tests. And then test custom. There we go. Obviously, we are going to want to. Did I comment anything more out here? I don't think so. No, did I already close off Godot? I didn't. I always want to make sure that I save it. Save and close. There we go. So that now means that I can go do this. Let's actually see. Yep. Let's just make that a new commit. Added support for added basic support for Omni lights to the alt.n shader templates. There we go. So anybody who wants to have a look at that code, you can just look at the example. So that's the address for the example. Yeah. I think we're going to leave it there, guys. I think that's it for tonight. So I hope everybody enjoyed that. I'm quite happy that I got through this and that I found some time to do it, because that was something that I had to do ever since Godot 4.3 was released, and I couldn't find time for it. So I'm glad that we picked some time here. But I'm going to call it there. I desperately need some sleep. I need to get up, like I said, very early tomorrow morning. Got a big day ahead of me. And yeah, thank you all for watching. And I hope to see you guys next time.